or Kendall, are you recording?
Recording in progress.
There we go.
Awesome.
All right.
Okay, so let me just start by turning on my camera. So, hi everybody. Good to see you all. And I will begin by pulling up my presentation. So, here we go. And let me see. Do you guys all see a slideshow called Bitvm Crash Course?
Yep.
Yes.
Excellent. Okay, so I prepared a presentation that hopefully will take us about 20 minutes to go through the presentation, and then an additional 20 minutes where I'll show you some code that I wrote recently that I tried to get working in Bitvm, and then I think we can do questions and have a great time. Sound good? All right. So Bitvm Crash Course is all about smart contracts for Bitcoin. And I'm going to begin, because I only have 20 minutes, I'm going to begin by making certain assumptions, which is, and the biggest one is that you guys already know how Bitcoin script works. And I don't know if that's true, but I believe some of you are stacks engineers, and if you're stacks engineers, you're probably familiar with scripting in general. So that's cool. And for the rest of you, hang on, because it's going to be a ride. Bitvm is based on two fundamental insights about Bitcoin script. One of them is that Bitcoin script can have state, which is represented by this filing cabinet over here with some data in it. And the other one is that Bitcoin script can compute. It's represented by the little computer. So I think most people are at least kind of familiar with what the concept of computing is, because we probably sit in front of computers all day, and we probably have computers in our pockets. But the concept of state might be a little less familiar to some of us. So let me give a description of what state is. If you have a Bitcoin wallet, one of the things you might do with that wallet is open it up and look at your balance. And your balance is like state in that app. It is a piece of data that sometimes varies, but that is meant to be interacted with by the user, or typically meant to be interacted with by the user in some way. One of the things that your app might have is a send button and a receive button, and those are supposed to be able to modify that state. If you hit those functions, your phone or your device should prepare to change your balance, and then if you actually send a transaction, it should deduct it, or if you receive money, it should increase it. And then some other functions of your device probably don't modify the state. Like maybe you can go into the settings and change from light mode to dark mode, and that shouldn't change your state at all. Bitcoin script can have state, it can have pieces of data that are modifiable by a program, and it can do computation. It can actually run programs that can modify some state. And those are the two fundamental insights that allow us to do smart contracts on Bitcoin. Before Bitvm, the blockchain was commonly thought of like this. Let me just make this a little bit smaller here. So it doesn't get in the way. It was commonly thought of like this. We got a couple of different transactions on here, and they've been thought of as discrete simple transfers from A to B. This little monkey doesn't know about this little monkey, and this little monkey doesn't know about this little monkey. Two transactions do not and should not know about each other for privacy reasons. And if you have data involved in transaction A, like maybe the public keys that control the money in address A, that data should not be available to transaction B. Transaction B should not know that transaction A has 5 public keys belonging to Alice, Bob, Carol, Dave, and Ed. That's how it's been thought of in the past. However, Bitvm changes all of this. Bitvm shows us that you can actually have transactions talk to one another. So we do this using hashes and preimages. Now this is where I think I'm possibly going to lose some of our less technical members of our crowd, but hashing functions are one of the core cryptographic primitives of Bitcoin and many other cryptocurrencies. And the Bitcoin scripting language, which is typically just used for sending money from A to B, supports cryptographic hashing as a primitive. So you can do stuff like you can say Alice is going to send some money to Bob, but before she sends it, she has to reveal a piece of data. She has to reveal the preimage to a cryptographic hash. And that's represented down here by this little monkey saying, here's the preimage, FDCB2FF. And that, if you run it through a hashing function, transforms into this other string, E65209. So you can reveal a piece of data when you're sending a transaction. You can say, all right, you know that I'm going to reveal the preimage to E65209, and when I do, then that's when the transaction becomes valid, and now I can send the money. So what we do is, to transfer state, we create two hashes, one representing the number 1 and one representing the number 0. And I keep getting a message that says my connection is unstable. Am I clear for you guys? Are you all able to hear me okay?
We lost you
For
for
the
a
most part,
minute,
but we lost
but
you.
we got you.
Yeah, we lost you for a few seconds.
Okay, let me move
But
to a place that's closer to the Wi-Fi, so that hopefully that doesn't happen again. Doing this at an Airbnb, and I'm not fully familiar with all of the dead zones in this place. Okay,
good.
hopefully that will make it less difficult. So you said you lost me for a few seconds. Let me restart part of this slide.
Yeah, we were there until I think you were reading out the hash and the preimage.
Okay. So this little monkey is going to send a message to this other little monkey, and in order to do so, she has to reveal a preimage to a hash. That's part of the script. It says Alice can only send money to Bob if she reveals this. If she reveals what data hashes to this value E65209. So she reveals that data, which happens to be FDCB2FF, and the little monkey on the other side, the recipient, can see that. She can say, oh, great, now I know that piece of data. So in Bitvm, we use that to transfer state between two transactions. You can create two hashes, one of them representing the number 1 and one of them representing the number 0. And you can make a script that requires you to reveal one of those two hashes. And if you do, then what we do is we check if the hash is equal to the value, and if it is, we use Bitcoin script to place a 1 where that hash was, and then if the other one is the one that they reveal, then we place a 0 where that hash was. And so I know that there's a lot of data in this slide, and I'm probably losing some of you as I speak, but I'm doing the best I can here in 20 minutes. We use another property of Bitcoin script to ensure that if Alice, the sender, reveals both of those preimages, if she says, I'm revealing both 0 and 1, then the recipient can actually take all of Alice's money. Like, she can take some collateral. And that ensures that she can only reveal one of these things. She can only reveal the 1 or the 0, but not both, which is important for some schemes. Sometimes you need to commit to a certain type of data, and if you reveal both, if you say it's both 1 and 0, it ruins things. So we can prevent that in Bitvm. But this allows us to actually transfer state between multiple transactions. If you can have 10 different transactions, all of which say that Alice has to reveal either the 1 hash or the 0 hash, or the hash representing 1 or the hash representing 0, and as soon as she reveals one, all of them can use that information. They now know something about the contents of another transaction, which allows our little monkeys over here to speak to one another, and that's pretty cool. Okay, so the next thing that is important in Bitvm is that Bitcoin script can compute. When you put data into a Bitcoin transaction and use it to unlock some money, it goes into something called a witness stack, which is an array of 1,000, I call them memory registers, an array of 1,000 memory registers, each of which can be up to 520 bytes. So here I've represented that by showing this bucket that has a bunch of data in it, and I'm just showing data number 21, data number 22, and data number 23. But all the data that you put in your Bitcoin transaction goes into this array, and then you can manipulate that data as part of unlocking this money to send it from Alice to Bob. You can use move operations to change the order of the memory registers. You can copy data from like data number 23 to data number 21. You could copy its contents from the one to the other. You can add. You could say like take the contents of data number 21 and add it to data number 22. If they're like both numbers, you can do that. You can subtract them. You can compare them. You can say, you know, if the number 5 is in data number 21 and the number 3 is in data number 22, you can ask it which one is bigger, and then, you know, maybe move the bigger one to the top, or maybe move the smaller one to the top, or whatever you want. But you can manipulate this data, and that allows you to do all sorts of computation. If you think about how computers are designed, they typically have something called an arithmetic and logic unit, which is used for modifying data, and then they have memory registers, which is like RAM, where they store data in intermediate values. So if you have the ability to move data around in an array and modify that data, you've got a little computer right there. So Bitcoin actually gives that to us. It's just built in part of Bitcoin, and you can use it. Also, Bitcoin has support for logic gates, which allows us to add pretty much infinite complexity to our Bitcoin transactions and to the unlocking scripts. So logic gates, for those of you who have not gone through Computer Science 101, are also called transistors in real-world computers, are the basis of how they work. Computers are mostly just a sequence of these connected little logic gates over it, and which I give some of the common examples of them over on the right. So the first one on the top there is called an AND gate, and all of the logic gates work on binary digits. They only involve zeros and ones. But the AND gate says that if you pass 2 ones to it, then it will output a 1. But if either of those are a 0, it will output a 0. Basically, it says the input number 1 has to be on, and the input number 2 has to be on, and then the output will be passed through. But if either one is off, then it won't. It requires A and B to both be on. The XOR gate, which is the next one down there, is kind of the opposite. It says if you can have the first one be on, or the first input be on, and the second one be off, or vice versa, you can have the first input be off and the second input be on, and in either of those cases, it will pass through a 1 to the other side as output. But any other situation, it won't work. If you have both of them are the same thing, like both of them are a 1 or both of them are a 0, then it says, no, that's no good. It has to be 1 on and 1 off, but in either order. The OR gate is kind of similar to the XOR gate, except it allows them to both be on. So in the XOR gate, or in the regular OR gate, if either one is on, like if the top one is a 0 and the bottom one is a 1, it's happy with that. If the top one is a 1 and the bottom one is a 0, it's happy with that. But also, if both of them are a 1, it's happy with that, and it will let a 1 go through. And then there's the NAND gate, which is the most powerful because it can simulate all of the others. That one is the direct converse of the AND gate. It will only allow a 1 to be produced as output if both of the inputs are 0. So these logic gates are the basis of computation, and in fact, all computers, like the computer in this machine that I'm working on and the computer in my pocket, those are just the CPUs themselves are just a sequence of connected logic gates. And since Bitcoin script supports all of the logic gates, it has this property called universality. Any program that you can run on any real computer, well, it's just passing electricity through a series of logic gates. So if we can do logic gates in Bitcoin, then you can run that same program on Bitcoin by just rebuilding the circuit that the electricity is passing through on your regular computer. And to illustrate this, I've I found this picture of an actual CPU that somebody took out of some device, and that's on the left there. This is what you might, if you took apart your computer, you'd see something like this in there. And the little silver piece that's on the top, if you take that silver cap off, what you'll see is this grid of logic gates. And we're going to zoom in on it here. This next slide is just the piece on the large one on the left is just a brightened copy of that of what's under that silver plate. And if we zoom in to the bottom left corner down there, and then zoom into that one's bottom right corner, you can see it's just a bunch of logic gates. And an individual one, it happens to be a NAND gate, is displayed up there in the top right. That is what they look like. And I use this to illustrate that your computer, all it is a bunch of logic gates, by which it does logic, connected up with some memory. So since Bitcoin has lots of memory that we can work with and shuffle things around in, and since it supports all the logic gates, you can do any sort of computation in Bitcoin. You could rebuild this CPU in Bitcoin and then run anything that can run on this CPU directly on Bitcoin. So that's the main premise of Bitvm. And then another important thing that we use in making this work is something that I call dependency chains. So Bitcoin supports this thing called multisig, where you can have multiple keys multiple keys control money in an address. And multisig allows us to sign what our transactions are. Like you can say the money in address A can only be spent if the full transaction is signed by key A and key B. And if you do that, anyone who's got a key in that address can force the money to only go to specified destinations. They can just create a signature that says this signature is only valid for a transaction that sends the money to address B. And as long as that's the only signature they create, that's the only place the money can go. As long as anyone who has a key only creates signatures that send the money to address B, that's just the rule. That's the rule for that address, or that's the rule for that contract. So we do this in Bitvm. We create these things called dependency chains, where if we want to do computation, we do part of the computation in address A. We supply inputs to a program, and the program is composed of logic gates, or shuffling things around in memory, or doing adding and subtracting and comparison. But it takes some inputs, modifies them in some way, and usually if it's a large program, you need more than one transaction to do it, because Bitcoin transactions can only be a certain size. So that's where we use state transfer. We modify the inputs and produce some output, and then we transfer that to the next transaction, which would be an address, by sending the money that's in address A to address B. And we require that once it's in there, you have to supply the same data that we just passed out of address A as input to address B, where the program continues. And the next part of the program modifies it again. And then we just keep doing that until the program is finished, until the program terminates, and we have our final output. So when we combine the fact that we can make dependency chains with Bitvm that has this ability to modify data and then transfer it from one transaction to another, we can combine those to do challenge and response, which is like here I show an example with checkers. You move a piece in checkers, and your opponent then has a chance to respond and move one of their pieces, and you keep doing this until someone wins the game. That's challenge and response. But it's also, challenge and response is also part of cryptographic schemes, like zero-knowledge proofs. You have a prover and a verifier. The prover makes some claim. The verifier challenges them to prove that claim, and you keep doing that. Like if they don't satisfy by providing a proof, if they don't satisfy the verifier, then the game fails, or the prover can lose some money. So this allows us to do we can do computation, and because we can do computation, we can do things like zero-knowledge proofs as well as games on Bitcoin. So in summary, Bitcoin script is more powerful than some folks used to think it was, because we've demonstrated that two or more parties can use it to transfer and modify state in arbitrary ways. And you can write programs that do this across many challenges and responses, many different Bitcoin addresses. And that makes Bitcoin super strong. Bitcoin's like this. I can do it all. I'm super powerful. So yeah, that is the basics of Bitvm. And I think the next thing I wanted to do at this point was demonstrate some code that I got running on Bitvm. I made a game of tic-tac-toe, or rather, I'm currently making a game of tic-tac-toe. And I wanted to show you guys my progress on it. Does that sound like a good thing to go to next, or do we have some questions that maybe you want to get clarified before we move to that part of the presentation?
Yeah, let's take one or two questions. Elena has a question, so why don't we start there, and then see if there's more before we move on.
Sweet. What's your question?
Well, first, I just want to say thank you. This is such a cool crash course. The two questions I had were one, just clarifying for dependency chains. With dependency chains, that was possible before Bitvm, right?
Yes.
So it really is just this conditional logic that you can use with multi-sigs.
Yes, except that also that was possible before Bitvm.
Yep.
Bitvm didn't
Mhm.
change anything in Bitcoin. We just kind of realized that if you combine the existing properties of Bitcoin, you can do arbitrary computation.
Okay,
But it
cool.
requires like three ingredients, which is the ability to transfer state, the ability to modify it, and this dependency chain thing, so that you can force the program to be distributed across multiple Bitcoin addresses if necessary.
Okay, yeah, nice. Um, And then my understanding is, so this is my second question. My understanding is that Bitcoin cannot read or understand anything that happens outside of Bitcoin or off chain. And so for a lot of these games, like when you mention it opens up the door for proofs, yeah, games and proofs, the assumption is that that you would put the proof in the Bitcoin block, and then the logic gate would verify, like, okay, is this proof valid? Yes or no, and then act on that, right? But the proof cannot live somewhere else.
The proof can start off somewhere else, but you have to put it in Bitcoin in order for Bitcoin to understand it. So with the example I'm going to show you with tic-tac-toe, Bitcoin doesn't know the rules of tic-tac-toe, but I encoded them I'm in the middle of encoding them into a project, into a Bitcoin address, or a series of Bitcoin addresses. And once I've got that, then those addresses understand, they understand the rules of tic-tac-toe. So then we can play it because now it's in Bitcoin and Bitcoin can use it. So yeah, you have to teach it because Bitcoin doesn't know the rules of any game or any challenge response protocol by itself. You have to teach it using logic gates.
Great, thank you.
You're welcome. Any other questions at this point?
I have a
Cool.
couple questions, but I think they'll be yeah, more appropriate after you go through the next section. So yeah, let's keep going. Thank you.
Awesome. Yeah, happy to keep going, and so let's do that. So the next thing, I'm going to share this link, and I'm going to warn you not to expect too much from this. I just created this repository right before we started this call, but let me share it in the chat. So go to chat, and I'm going to drop the link in here. Link to, I'm going to put it in caps, work in progress, Bitvm based tic-tac-toe. So there you go. You guys can click that link to join me on this page. And like I said, don't expect too much on here because it doesn't work yet. But I'm going to show you with caveats and with the difficulties of something that barely or only partially works, how Bitcoin can understand the rules of tic-tac-toe without actually having tic-tac-toe in it. So we start off here with a grid, and if you click these things, nothing happens because we haven't started playing yet. And I'm also going to open up my browser console. If those of you who want to follow along, it'll be important that you do this as well because all of the state is going to be displayed in our browser console here. You can do that, or at least in Firefox, by doing Control-Shift-I. We'll open that up. I think in other browsers and in Firefox, you can also go to Tools, Web Developer Tools, and that should open it up for you. You might have to click the Console tab at the top of this thing. But this is where we're going to display some of the state in our project. And the other thing I'm going to do is I'm going to open up MutinyNet. MutinyNet is one of Bitcoin's test nets. It was created by a friend of mine. Anyone can create a test network on Bitcoin that follows Bitcoin's rules, but the money's fake. And this guy, one of my friends, created MutinyNet, where blocks come in every 30 seconds, or about every 30 seconds, which is really nice for testing because working on Bitcoin, the blocks come in every 10 minutes, and if you're doing stuff like waiting for someone to finish their move, it sucks to wait 10 minutes. So I recommend that you go to this website, but specifically, we're going to be using this part of it where you broadcast transactions, because we're going to be broadcasting some raw transactions here. I know, this is terrible user interface. Well, it's not finished yet, so that's why that is. So I'm going to share this link because we'll be using this link to broadcast transactions, and those transactions will be showing up in our browser console. And then the other thing we'll need is the faucet, because the coins are fake and they're not really worth anything. We have the ability to he just gives them away for free on MutinyNet. So if you go to this link, link to the faucet, then you can follow along by actually sending money into this thing, into the Bitvm contract that I'm about to show you. Okay, so I'm going to first start off by clicking play, and almost immediately you're going to notice that it gives you a little prompt. It says, please send money to this Bitcoin address and enter the transaction ID. Now, once again, I know this is not something that anyone would actually play like this, because this is horrible, and people can't be expected to be copy pasting things from faucets and whatever. But I'm in the middle of building it, so this is what you get when this is how the sausage is made, at least when Super Testnet's doing it. So I'm going to go to this faucet. I'm going to say I want to send 10,000 sats into this Bitcoin address, which is going to be controlled by one of the parties to our contract. And let me do that. So I've done it. And money is in that Bitcoin address. And I'm going to view it because I need the TX ID. So, oops, no, don't go to Twitter. Here's the TX ID. You can also get it from right here by clicking that. And I'm going to paste that into where it says to. Then it wants to know something called the VOUT, which this Bitcoin transaction sends money from this address to my address, and it sends the change back to the faucet. The VOUT is which one of these is the one we want, and ours happens to be VOUT number 0 because they're indexed from 0. So the first one is the one we want, and so we put a 0 in where it says the VOUT. And then it wants to know the amount. I happen to send 10,000 sats into this Bitcoin address, so now it knows the amount. Okay, so what it wants us to do is there's like conflicting instructions on screen now. I apologize. But there's one that says broadcast this transaction. That's going to initiate the Bitvm contract, which has the rules encoded in it. And we'll be dissecting this, and I'll show you what it looks like. But first I want to actually play a game so you can see how it looks. So we copy that transaction from the console and broadcast it, and it gives us a little TX ID showing us that it's happy. If there was an error, it would be red, and it would tell us that the transaction was wrong for some reason. So the contract has been initiated. There's money in a Bitcoin address that knows the rules of tic-tac-toe, or at least some of them, the ones I've written so far. And now we get an instructions that says, please place an X. So we pick a spot to put an X. I'll just put it up there in the top left corner. And when we do, it creates a new Bitcoin transaction, which is in our console. This one's much, much larger. And we can, well, I'm going to actually open up this one because this one's important to dissect so we can see how this works. But I pasted it, and let's take a look at this transaction. And you can notice it's larger than a normal Bitcoin transaction. Most Bitcoin transactions, they just have, the sender, the recipient, and a signature and an amount. And this one's got a bunch of stuff in it. Like it's got a pre-image here, and it's got a long script, and it's got this big chonker down here, which is called a control block. But yeah, I'll explain more, and it's got 2 signatures in it because this is a multi-sig. Alice and Bob both have a key, and they both have to provide signatures for the dependency chain. So that's what all that data is, but we're going to look into it more in a minute. But the point is that inside of this transaction, one of the things that's in it is, let me click details on it, or not that one, this one. one of the things that's inside is this little pre-image. And this is, if I can zoom in on it, this is the piece of data that Alice reveals, and it corresponds to which square she picked. She picked the top left, and so she revealed a pre-image that she only reveals if she clicks the top left square. And she's got 9 different pre-images she can reveal in her transaction. So there it is. I'm copy pasting it from my console, but in reality, if you were doing this on Bitcoin, her opponent would get it from the blockchain. And then I'm going to paste it into here. So this is Alice's move, and you click OK. And in the console, you can see a representation of the little board. Bob now knows that there's an X in the top left corner because that's the pre-image she revealed, and he is now instructed to place an O. So it's Bob's turn. So I'm just going to place an O right here in the top middle, and then mostly the same thing happens. He has to broadcast a transaction, so I'll do that, and then we'll take a look at it. And if we open this up, it's similar to the other one in that there's 2 signatures that enforces the dependency chain. Now there are 3 pre-images. I'll explain what those are in a minute. There's the script. This is the rules of tic-tac-toe are in this little block right here, and a control block, which I'll also explain a little bit later. But there are three pre-images, and the one that reveals Bob's move is, I think, this one, 92F. So no, that one is him accepting Alice's move. So in this game, I had to. Well, I'll show you this in the code a little bit later. But I had to make it so that Bob acknowledges Alice's move. And he does that using this pre-image. It's called the accept pre-image, where he says, okay, I acknowledge that you have the top left square, so I can't pick that anymore. And if he does, if he tries to pick the top left thing, Alice can prove using this pre-image that he's breaking the rules because he knows that one was taken. Then his move is 1FD, which is also on the blockchain right here, 1FD. So Alice, she would be getting this from the blockchain, but here I'm just copy pasting it from my console. So Alice has to paste in Bob's acceptance message or acceptance pre-image, where he's saying, I understand and I accept that you've taken the top left. Then she takes his move, and now in her little representation on here of the game board, she can see that there's an X and an O, or that her X is in the top left and his O is in the top middle. And then they basically just keep doing this. She can place an X wherever she wants. He can keep going, or he can do the same. He can place O's. One thing, and the nice thing is that I've found that there are 5 ways to cheat in tic-tac-toe, and they are: A, you can stop playing. You can just abandon the game halfway through, and that's cheating, because when you play a game of tic-tac-toe, you're agreeing to play it till the end, at least in this version. You can overwrite an existing square, so like Bob or Alice, who's X, she could try and place an X over Bob's O, and I have a fraud proof to prevent that. That's why I need them to each acknowledge each other's transactions. Another thing you can do is try and overwrite one of your own squares. I don't know why you do that in tic-tac-toe, because it's basically skipping, but it is against the rules. So I made it so that if you overwrite your own squares, I have a fraud proof for that allows the other person to take your money. So that's 3 ways you could cheat. A 4th way is by trying to take a move twice in the same turn. So Bob could reveal a pre-image for both, or Alice rather. She could reveal an X for here and an X for the middle in the same turn and try and claim both those spots. So I have a fraud proof that prevents her from doing that. If she does, Bob can take her money. Same with Bob. If he tries to take 2 turns in one move, Alice can take his money. And then the 5th way you can cheat is by claiming you've won when you have not. Claiming that you have 3 in a row, or 3 down, or 3 diagonal, without the ability to prove that. And if you do that, then your opponent can take your money as well. So I think this game, I haven't encoded the rules for winning yet. So if you play this all the way through, even if you get 3 in a row, it won't detect that, and you can just still keep going. So that's it's a work in progress. But I think you can kind of get an overview of the fact that what we're doing is we're revealing information, and we're passing that between two different Bitcoin users, so that they can use that in their own transactions to make additional Bitcoin transactions and continue the game. So I'd like to show you some of the code for how I'm doing this, and this is the code on the screen here. So I would eventually I'm going to make this into a workshop where we'll actually build it together, and we'll be like doing the things where we're creating the fraud proofs, interactively. That's not ready yet, and the game's not even finished yet, so I'm not there yet. But it needs 3 dependencies, one of which is a library for working with Taproot transactions, and that's what manages control blocks and stuff. Hopefully I'll tell you about that in a little bit. It needs a library for working with Bitcoin's elliptic curve, which is the SecP256K1 curve. I'm using a library called Noble SecP256K1. And I need something for doing hashes, because we use hashes and preimages to reveal data about the state of the game. So that's what this library is. I'm using the RMD160 hash function, and that's so I imported a library for that. Another thing I need is combinatorics, which is a mathematical concept that allows you to take a list of items, and then you can say, I want to get every pair of items from this list with no repeats. And we use that for something I'll show you a bit later. But this script tag here is an open source combinatorics library I found for JavaScript. And I couldn't find a packaged version of it, so I just copy pasted the code into my browser. Then there's some style tags which create the game board and make it look like a tic-tac-toe board. There are some functions in here for grabbing information from the URL, which I'll eventually use for Alice and Bob to share public keys with each other, as well as a few functions here for transforming hex into bytes, bytes into hex. Bitcoin likes things to be in hex, but JavaScript wants them to be in bytes, or at least some of these libraries want them to be in bytes, so I have to convert between those. And then the RMD160 function that comes from the library I imported earlier. A function called wait_a_sec, which allows me to do a loop where I'm waiting for someone to input data. I can just wait till they do that. So I have this function called wait_a_sec. And wait for move, which is just a wrapper around it. It waits until they make a move, and that's what that does. So the important stuff is down here. The page starts out with a contract, which is empty, in an empty array. Actually, I should increase the size of this so you guys can see it. Sorry about that. So it starts off with an empty array, and as we create these Bitcoin transactions, it adds them to this contract. This is where the dependency chain goes. It says Alice has to send the money to Bob, has to send the money back to Alice, has to send the money back to Bob, and if either of them tries to just take it, well, they can't, because they're multi-sigs. You need both signatures, and so they force each other to send the money, like only to proceed through the game. And then if either of them stops, I have a thing for that I'll show you later. So that's where the contract goes, with the dependency chain. I call the dependency chain the contract because it includes the whole program. Then there are the hashes, which are what Alice and Bob are revealing to each other. They're revealing the preimages to hashes, but we dump the hashes into this array as they are revealed. We have a little flag that says fraud occurred, true or false. If this ever gets triggered, then the game stops and it tells you how to take your opponent's money. We have 2 objects. One of them is Alice, and she's got a private key, which it's not a secure private key. It's just the letters AB repeated 32 times. That's her private key, because work in progress. It's not secure yet. And it's got the scripts she's going to use for encoding the logic of this game, which there's nothing in there yet because we haven't started. We have to click the play button before any of this gets filled out. It's got this thing called trees, which are a part of TapScript. When we encode logic into Bitcoin using the TapScript upgrade, we create a tree of all the possible game states, and we hash them all and put them into this little brackets here. There are the pre-images and the hashes, which I mentioned earlier. You disclose the hashes ahead of time so that you can create the contract, and then you reveal one pre-image per turn, corresponding. Well, sometimes you reveal multiple, but you reveal at least one pre-image per turn, representing where you're putting your X or your O. Then we've got the accept pre-images and the accept hashes, which are how you acknowledge the other person's move, and you have to do that before proceeding. You have to say, all right, if they pick square number 1, I'm going to accept that they click square number 1, and if you don't accept it, then you lose your money, which I'll show you how we do that later. Alice keeps track of Bob's moves, as well as which squares Bob has put O's in, and she also keeps track of Bob's acknowledgments, of Bob saying, yeah, I acknowledge that you picked, that there's an X in this square over here. Okay, so that's what Alice is, and then the other thing we do is we give her a public key by running her private key through the elliptic curve and getting its corresponding public key. And that controls the multisig. We create the funding address, which is the first thing. It said, like, first send money to this address. I have Alice do that. So she in this version, Alice funds the contract. She puts money in, and she's saying, I'm going to win at tic-tac-toe, otherwise you get this money. I think when this is finished, I'll probably want to have that be, they'll both have to deposit funds, so that they're kind of saying, if there's a tie, we get our money back, and if Bob wins, he gets everything, and if Alice wins, she gets everything. But for now, I'm just having Alice fund the whole thing because it's easier. So we've got these things are for Bob to keep track of Alice's stuff. He keeps track of the latest pre-image she's revealed, the latest hash that it corresponds to, and her most recent move. He dumps those into there. And then we have the same thing for Bob. He's an identical object to Alice, and he's got the identical things for her to keep track of where he's doing. So the next thing we do, after we've got these objects prepared of Alice and Bob, is we fill up their hashes and pre-images section. Each one has these two fields for pre-images and hashes, and we fill them up. We create a bunch of pre-images, and here we create 45 of them, and we add them to Alice's object. We just push each pre-image. That's the secret that she reveals when she's picking a square. We also hash those pre-images and then put the results, put the hashes into her hashes array. So she ends up with 45 pre-images and 45 hashes. Why 45? Well, in this game of tic-tac-toe, Alice takes 5 turns. She's placing X every time, and you can take up to 5 turns if you're X, because there's 9 squares on the board. She goes first, and it alternates. So she puts one, then Bob places an O, then she places an X, and she can do that up to 5 times. And then there'll be 5 X's on the board and 4 zeros, and there's no more place to put anything. So since she has to reveal one position on the board 9 times, or five times, and there are 9 spots on the board, I multiplied 9 by 5 and got 45. And that's how many pre-images she needs. Same thing for Bob, except he only gets 4 turns, so I multiplied 9 by 4, and then he has 36 pre-images that he can reveal. He reveals at least one for each turn. Then Alice has to be able to acknowledge that Bob's squares are taken, so every time there's a 0, she needs to be able to acknowledge that, and that's why she also creates 36. So up here is where Alice creates 36 acknowledge pre-images and acknowledgement hashes, and then down here is where Bob creates his 36 pre-images and hashes. And then Bob also creates 45 acknowledgement pre-images and hashes so that he can acknowledge when Alice has placed an X in a square. And he has to do that up to 5 times. And there are 9 possibilities, so that's why he needs 45, because 9 times 5 is 45. So that's where all the pre-images and hashes go. Then I've got the fraud proofs. So there's 3 functions down here called prove double turn, and then down further below, prove overwrite self. That's where if you try and basically skip a turn. I don't know why you'd want to do that, but I needed to have a rule for it so that they can't do it, because you're not allowed to do that in tic-tac-toe. You can't skip a turn. And then overwriting your opponent. So we have these 3 functions that are the main types of fraud you can commit. And then the other 2, besides overwriting and saying to take a turn twice, the other 2 you can do are abandoning the game or claiming you won without the ability to prove it. So I have different functions for dealing with those, but these three fraud proofs are where we use the combinatorics. So what we do is we take every hash that corresponds to one of the squares on the board, and we make it so that we can prove someone took a double turn if if they reveal 2 of the first 9 hashes. So Alice, if she has to reveal 1 of the preimages to her first 9 hashes, and that corresponds to which square she's picking. If she reveals 2 of them, that's like trying to take 2 squares in the same turn. And if she does that, Bob needs to be able to take her money. So we take all of her 9 hashes, and we use combinatorics to say if she reveals any 2 of them, Bob gets to write this script down here, where he can show that he knows 2 preimages from her first 9, from her first set of first 9. And if he knows 2 of them, that means she tried to cheat. She tried to take 2 turns at once. So we give Bob the ability to take her money. And vice versa. If Bob does it, Alice can do the same thing. So combinatorics lets us do that. And we use it again in overwriting yourself. If you can overwrite yourself by revealing square 1, for example, in turn 1, and then in your next turn you reveal square 1 again. And that would be overwriting yourself. So what we do is we get all of the hashes that correspond to square 1, and then we add 9 to it to get the hash corresponding to the square 1 in the next turn. And we do that for every square. And then if, down here, if Bob learns 2 of them, if he learns that Alice took square 1 in turn 1, and then she revealed the preimage for square 1 in her next turn, he now knows 2 of her preimages for the same square, and that proves that she tried to cheat by overwriting her square. So we just let Bob take the money, and vice versa. If Bob does it, Alice can take the money. And we do a similar trick for overwriting. If you overwrite your opponent, basically for that one, we use the acknowledgement. Whenever Alice takes a square, Bob has to acknowledge it, and so he has to reveal that to Alice, otherwise he can't take his turn. And once he does that, she knows that he has accepted that she has square number 1. So if Bob then puts an O there, she can say, but I know you accepted that I have square number 1, so here's the acknowledgement preimage that you showed me, and here's the preimage where you tried to take number 1. And so down here, if she knows both of those, she can prove it and then take Bob's money, and vice versa. If she does it, Bob can take her money. So those are the 3 main forms of fraud, and those are the ones I've implemented support for. The other 2 are abandoning the game and saying you won without being able to prove it. So for abandoning the game, that one's pretty easy to deal with. I do that right here. So I have a script that says if 10 blocks go by and Alice doesn't make a move, if Alice doesn't move the money to the next address, we put Bob's pub key on the stack, and then we run a check sig on it. So he can just specify where he wants the money to move. So this one prevents Alice from abandoning the game. If she does, after 10 blocks, that's what check sequence verify does. It checks that a sequence of 10 blocks has passed. Bob is able to take the money. So, Alice has got to be quick. If she abandons the game, she loses it. And there's a corresponding Bitcoin address, or the Bitcoin address that we put money in when it goes to Bob, has a similar thing here that lets Alice take the money if Bob abandons the game. Up here, one of these scripts is the happy path. This is called a multisig, and it's got Alice's pub key as well as Bob's pub key in it. And they use this to send the money on through the dependency chain from one transaction to the next. And so that's how the dependency chain is enforced. It also lets them, eventually this will allow them to play the game off-chain. So once they deposit money into the Bitcoin address, they don't have to keep sending it back and forth between each other. They can just reveal their preimages to each other for what moves they're making. And if they agree on the outcome of the game and they say, yeah, Bob won, they can use this multisig path to just sign and send Bob the money without playing it on-chain. And this is one of the important factors about Bitvm. We designed it so that when you're doing these contracts, you don't have to run the program on chain. You can run the program off chain by just revealing the data to each other, and then you save a lot of space. Like there's only two transactions: the funding transaction and the withdrawal by whoever won, and that's great. Then you save a bunch of space by not putting the whole program on the blockchain. But you have to be able to put it on the blockchain in case either party tries to cheat or stops playing or whatever. You have to be able to play it out so that you can prove fraud. So that's why we have all of those fraud-proof stuff, is so that you can use them if necessary. But ideally, especially in something like tic-tac-toe, no one's probably going to cheat at this, so because they know they'll just lose. But yeah, I think you can see from this, there's certainly a lot more code to make this thing work. But I hope that I've illustrated the principle of how you can, of the things that make Bitvm work. You're revealing information to your opponent that they can use in their Bitcoin transaction to ensure that you're following the rules of your game. And I encoded at least most of the logic of tic-tac-toe. I haven't done the part where you can win yet. But I've encoded most of it in a way that Bitcoin can understand, using hashes and preimages and combinatorics. And we can do that in Bitcoin because we can do combinatorics by moving things around on the stack, and we can do logic. So we can just check if he has 3 in a row or something, if either party has 3 in a row. So that's how Bitvm works.
Super cool. Sorry to interject, Super Testnet. We are coming up on time here. We have about 5 minutes and a couple of questions, and I'm sure folks have more questions. So if it's okay with you, could we transition to Q&A?
That's what I was just doing. I was wrapping up and just going to say, so that I can't show you everything, but you can look through the code. So far it is about 1,500 lines of code, or 1,600. And you can let me know if you have questions, but it is in a work in progress state. Any questions?
Well, this is fantastic. Thank you so much. Elena has a question, and then we'll see if we have time. We'll take more. Go ahead, Elena.
So the game you illustrated was between two parties, and I had a naive understanding that like this first kind of version of Bitvm is just between two parties, but people are working on making Bitvm usable for games with multiple parties. So I'd just love to hear you explain that or help me understand that better. And then one of the big value propositions that people are excited about with Bitvm is this N of 1 honest minority assumption. And you were talking a lot about how you can't cheat in these rules, and you've created fraud proof so people can't cheat. So I'd love to hear kind of you talk about those two topics.
Yeah. So when I showed you this multisig that enforces the dependency chain, enforces the money to proceed through this contract, you can have more than 2 people in a multisig. You can have, I think it's something like 67 is somewhere close to the maximum number of people that can fit. So yeah, you can just do that, and then as long as one of those people is willing to send it to the next transaction, the only way, once it's in the next address, the only way to keep the game going is to play the game. Like you have to make a valid transaction that spends the money. Or you can have everyone in the multisig agree to send it somewhere else. But yeah, that's the other thing that can happen is you get slashed. You can have any of the parties can just take the money if the person who's not doing it correctly cheats, or if he abandons the game or whatever, if he stops following the rules. So yeah, the honest minority assumption of you only need one person to be honest comes from the fact that you can just fill up this field right here with a ton of public keys, and as long as one of them is willing to only sign transactions that move it through the series of transactions that moves it through the contract, then that's the only thing it can go. That's the dependency chain. Then it makes it work. You just have to have one of them be honest. So yeah, that's how that works. Any other? Did that answer your question, or is there more to it than that?
Nope, that was perfect.
Cool.
Anyone have any other questions?
Yeah, I just had a very quick question. First of all, this was great. Thank you so much. So I noticed that once you started playing different turns, the code that you were broadcasting on transactions got larger and larger.
Yep.
I'm wondering what would happen if there's ever a need to write a program that's very complex, so it requires large amounts of code. Like, how would Bitvm deal with like block size constraints? Is there a way to split the logic across different blocks or something like that?
Yeah, there is. So you can. I showed you earlier how you can transfer state between two different Bitcoin addresses. So what you do is you create address A that has some part of the program. Provide inputs to it, and it runs some of the logic, and it produces outputs. And you require that in address B, the outputs from address A are used as inputs to address B. And then you can use a time lock to make it so that address B has to be in the next block, or some block after the one that address A was in. So that allows you to split it across blocks and get around the block size constraint. You can just transfer the state over to the next one and keep running the program. Does that make sense, my friend?
Yeah. Perfect. Thank you.
You're welcome, Elena. Elena says this is the clearest explanation I've heard. Janik says, who's going to build the assembly or C to Bitvm? We've got people working on it. I have written an assembly thing. I've written a thing that you can write assembly for Bitvm myself, but it's not the full set of assembly. It's only like 15 commands of assembly. So we've got it does work. Like you can write, if you can fit an assembly program into these 15 commands I implemented, you can run them on Bitvm. But we need people to add additional commands to it so it can do more. The amount of things Bitvm can do keeps growing every day. Like it's almost ready to do tic-tac-toe, which is pretty cool. Any other questions? Or I guess we're out of time, so that's probably it.
Yeah, we are at time. I'll follow up with you offline with some questions I had, but again, thank you so much for coming out here, and it seems like folks enjoyed it, so really appreciate it, and thanks also for letting us record it.
You're so welcome.
Grateful. Yeah.
I'm glad you guys enjoyed it. Thank you so much for coming, and I'll stop the recording here as well.